All right, so in this section 11.6, we're going to look at how do we find an area of a regular polygon. So the first thing I want to do is show you this picture right here. So I took a picture of a hexagon that I made, and if you notice, it's kind of made out of a bunch of little triangles. So we are very familiar with triangles. And the way that we're going to approach finding areas of regular polygons is we're going to break them up into triangles and approach it that way. Now, before we find any area, what we want to do first is make sure that we are familiar with all the terminology or the words that are going to show up in this section. So let's take a minute and kind of skim through the definitions. And what you can do is pause the video and just read through, and this is also in your textbook. All right, so let's take a look. So the polygon that we have is inscribed in a circle, right? And then we're talking about the center of the polygon and the radius of the polygon are the centers and the radius of the circle. So here's your center, right? So the center of the polygon and center of the circle are the same. Also, we have this word radius, which we have seen in circles, but now we're going to see it when we talk about polygons. So when somebody says, what is the radius of this polygon, they're really talking about the distance from the center to one of the vertices. Okay, so for example, in my picture, in my little yellow hexagon that I made for you, the radius would be this distance right here, right? So it has to go to the vertex because it actually has to touch the circle. So this little guy is going to be a radius of the polygon. All right, so then there's another word. It's called the apothem or apothem. And it is going to be the distance from the center to any of the sides of the polygon. So here in our book, they drew this for you. So it goes to the center of the side. On my hexagon, it would be from this center. It doesn't go to the circle anymore. It's going to go to the middle of my side. And since this polygon is regular, it doesn't really matter which side I go to, right? It's going to be the same. And it has to be perpendicular to the side. So this is your apothem or apothem, whatever you want to call it. Okay. And essentially it's going to help us because the apothem is the height of the triangle. So when we're looking for areas of triangles, the height is going to be really, really important to us. All right, one more word that will show up here is the central angle of a regular polygon. So when we talk about a central angle, it is the angle formed by the two radii, right? So for example, if I take this radius, right, it has to be a consecutive vertex. So then let's say I go to this vertex. So this right here is the central angle that they're talking about. So for example, if I go to my hexagon and I want to find the central angle, so I'm going to look for this angle right here, right? Okay. And again, right, so they kind of give away how to find the measure of the central angle, but if we just think about the fact that we hopefully all remember that there are 360 degrees in a full circle. So if I have a hexagon, for example, all I would do just to find a central angle is I would divide 360 by the number of sides because that's how many angles I can have. Okay. And that's pretty much it. So those are the terms that show up. So on your Google form, you're going to see some of this terminology. So now let's go ahead and actually find some links and some areas. Okay. So this is the sheet that was linked in the plan. So if you have a printer, you definitely can print it, but you don't have to. You can just take notes. So here is a regular octagon, right? So octagon has 8 sides and it's regular. So the first thing that we're interested in finding is the measure of angle EOK. So let's take a look. So EOK would be this angle right here. Now, it's not the central angle, it's half of the central angle, but then we'll talk about why this is important in a little bit. So let's just think about it. We're going to take a look at our octagon, right? So we know that there are 360 degrees in the full circle, and an octagon has 8 sides, right? So this is going to give us our central angle. So if we do 360 divided by 8, I'm going to grab my calculator. We get all right, so according to my calculator, it's 45 degrees. So that would be the central angle. But my angle, EOK, is half of that, right? So we're going to do, so this is your central angle. And then just on my picture, just so you understand the difference. So the central angle would be the angle between the two consecutive radii. So this would be our central angle, right? But I'm going to only find half of it, and that's going to be relevant when we start looking for lengths, because we specifically are interested in a right triangle. So I'm going to do, so measure of angle EOK is going to be half of that. So we're going to do half of 45. And half of 45 is going to be 22.5 degrees. So this angle that we have right here is 22.5. Okay, so then we're going to start getting some numbers. So then it says, well, if OE is 10 centimeters, so 10 centimeters, right? So, and that's also going to be called the radius of your polygon. How long is KE? Right, so we're going to have to use some trig here, right? So what we're going to do is we're going to focus on this one triangle, one at a time. And if you notice, so if you kind of compare this triangle and this big octagon, so this triangle is this right here, right? So we just kind of made it bigger to help us out. So I'm going to erase the yellow marks. I'm going to transfer some numbers. So we found this angle here to be 22.5 degrees. And we are asked to find KE. So I'm going to call this X. And I'm going to move this over to give us space. Okay, so we definitely need to have, we definitely need to know our trigonometry. So we're going to have to use one of the trig ratios, either sine, cosine, or tangent. So I'm going to write this down for our reference. All right, so let's take a look. So we definitely have the hypotenuse, and we're interested in the opposite side. So I'm going to use the sine ratio. So sine of 22.5 degrees is opposite over the hypotenuse. So x is going to be 10 times sine of 22.5 degrees. And you have to make sure your calculator is in degree mode in order to do that. And I get approximately 3.8268. So I'm going to say 3.83 centimeters for this one. Okay, so we're going to go back and we're going to say 3.83. Okay. Now we're interested in OK as well, because that's going to be important for our area. Now OK is this, and that is our apothem or apothem, right? So whichever way you want to call it. Okay, so I'm going to call it Y, and we're going to use trig as well, right? So in order to find Y, I'm going to use my 10 centimeters again for hypotenuse, but now I'm interested in adjacent side, so I'm going to use the cosine ratio, and it's y over 10. So y is going to be 10 times cosine of 22.5, Again, you want to make sure that you are in degree mode to ensure that your calculations are precise. Okay, so I get approximately 9.24 centimeters. So 9.24 centimeters. So let's go back. 9.24 centimeters. Okay. So honestly, this was the hard part, the angle and then the two side lengths. So now that you have everything, right, we want to find the area of this one triangle OKE, right? So that's this guy right here. So I'm going to just do my work underneath right here. So let's just think about it. We just spent a whole week on finding areas and perimeters. So this is a triangle. So the area of this triangle is going to be 1/2 base times height. And the base is 3.83, which is what we found earlier. And our height is 9.24. And approximately we get, let's see, I'm going to do my calculations. And your numbers might be slightly off, really, depending on how you round. So 17.7. It's 17.69, but I'm just going to round it to 17.7. So that's going to be my area. And that's going to be centimeters squared. So now that you know an area of this one triangle, you can definitely find the area of the whole octagon. So an octagon has 8 sides, and 2 of those little triangles fit into, I guess, along each side. So altogether, you would have 16 of these little triangles, right? So we have 16 triangles, and each area of one triangle is going to be 17.7 centimeters squared. And then if we do our calculations, I get 283.2 centimeters squared. And that would be the area of the entire octagon. All right, so in this approach, again, there is the special formula for the regular polygons. We haven't used it yet. We just broke it up into a shape that we already knew how to work with, a triangle. And we found everything that we need just by breaking up the octagon into 16 triangles that are identical, and we looked at we just looked at one of them, found everything we needed to find the area, and then we were able to use that in order to go back to our octagon and find the total area.